All right, welcome. Today, we're going to do something a little different. We're moving beyond just patching up code. We're going to learn how to think like a real software architect. That means breaking problems down to their absolute core, using something called first principles. This, right here, is the leap from just writing code to designing truly elegant solutions.
And this quote, yeah, it really nails it. See, we're not just banging out lines of code and hoping they work. We're designing a structure, a system. True architectural thinking, it means you start at the rock-bottom foundation of a problem. You build something that's not just functional, but also, elegant and super efficient.
Okay, so why bother, right? Why do we even need to think this way? Why not just jump straight into coding the solution? Well, here's the thing. Understanding the why behind the code, that's what separates a good coder from a truly great architect. It's all about seeing the big picture. So let's zoom out for a second and see what that looks like. Look, I know what you're thinking. Extracting the last digit of a number sounds kind of trivial, right? But trust me, this is a fundamental skill. It's like the secret handshake to get into more complex stuff like number theory and even cryptography. And modularity, using functions, what's that all about? It's just smart delegation. I mean, you wouldn't want the CEO of a company sweeping the factory floor, would you? Of course not. And that exact same idea applies to writing clean, well-structured code. All right, every great architect needs a blueprint, a plan. So let's lay out the specific mission we've been given today. Now, on the surface, it's going to look pretty simple. But there's a catch, a crucial constraint that's going to force us to think like an architect.
And here it is. Our goal, take two numbers, grab their last digits, and add them up. Simple enough. The numbers can be pretty big, but they're just normal integers, so no tricks there. But here's the big one, the key architectural constraint. All the real work, the calculation, it has to happen inside a special function. The main part of our program, it can only be the manager, the coordinator. It can't do the heavy lifting itself. And this is what forces our hand. It makes us be good architects.
So to tackle this challenge, every architect needs the right tools in their toolkit. And our first and maybe most important tool is one that lets us literally take numbers apart. So let's talk about the magic of the modulo operator.
The modulo operator, yeah, it's that percent sign. It sounds super technical, but its job is ridiculously simple. It just finds the remainder after a division. That's it. And when we use it in a very specific way, when we divide by the number 10, it does something, well, kind of magical for us.
Just look at this. 42% 10. What's left over? A 2. 59% 10. You get 9. Even a nice round number like 100, when you divide by 10, what's the remainder? It's 0. Are you seeing the pattern here? In every single one of these cases, the remainder is the last digit. It's that simple.
Okay, let's use an analogy to really lock this in. Think of the normal division operator, the slash, as a greedy banker. You give him 42 rupees. He only cares about the big 10 rupee notes. He's going to take the 40 and leave. But the modulo operator, the percent sign, he's the chiller collector. He completely ignores the big notes. All he wants are the leftover coins. So from 42, he grabs that 2 rupee coin. And for our job, we want those coins. We want that remainder.
So listen up, because this is the golden rule right here. This is the crucial takeaway. If you want the last digit of any integer, doesn't matter how big, you just do modulo 10. That's it. That's our first principle for taking numbers apart. Lock this concept in your brain because you've just mastered the first half of our mission.
Okay, awesome. We've got our tool for breaking down numbers. Now, let's talk about the second big principle, structure and delegation. And for this, yeah, let's bring back our friendly neighborhood CEO.
Remember that factory analogy? Well, the main part of our program, that's the CEO. And a smart CEO doesn't run around trying to do every single job on the factory floor themselves, right? I mean, that would be total chaos and super inefficient. Instead, what do? They delegate. They give specific tasks to specialized workers. And in the world of code, those specialized workers, we call them functions. Now, to use a function the right way, there are basically 3 steps you got to follow. First up is the prototype. This is like putting out a memo saying, hey everyone, this new specialized tool now exists. Then you have the call. This is the moment our CEO, our main function, actually points to a task and says, you, specialist, go do this. And finally, you have the definition. This is the detailed instruction manual for the specialist worker explaining exactly how they get their job done.
All right, let's recap. We have our principle for taking digits apart. That's modulo.
And we have our principle for organizing our work. That's functions. Now it's time to put them together. We're moving from the blueprint to the actual build. Let's get this thing built.
First things first, we lay out the blueprint for our specialist worker. We tell the system it's going to return a whole number, an int. We give it a descriptive name, some last digits. And we tell it exactly what it needs to do its job, 2 numbers, which we'll call A and B. This whole line, this is what we call the function's signature.
Okay, now for the magic inside. This is the core logic. Inside our function, we use our golden rule. We grab the last digit of A using A%10. We do the exact same thing for B. Then we just add those 2 digits together. And the last step, we return that sum right back to the CEO who asked for it. See? It's simple, it's clean, and the task is perfectly delegated.
So what's left for our CEO for the main function? Well, its job is now super clean and simple. Its only tasks are 1. Get the numbers from the user, 2. Call the specialist function to do the hard work, and 3. Print whatever result that specialist sends back. This is what modularity is all about. It's organized, it's easy to read, and it's incredibly efficient.
You know, the brilliant physicist Richard Feynman had this famous test. He said if you can't explain something in simple terms, you don't really understand it. So let's do a quick Feynman checkpoint right now. Let's test our new architectural knowledge and see if we've really grasped these first principles.
Okay, first question. What is 1, 2, 3, 4, 5% 10? Think back to our golden rule, the one about remainders. What do you think? What's the answer going to be?
It's 5. That's exactly right. The modulo operator just plucks that last digit right off. Doesn't matter how big the number is. Perfect extraction every time.
All right, next one's a little trickier. Let's put the whole system to the test. If our CEO, the main function, passes the numbers 110 over to our specialist function, what's the final value that function is going to send back?
The answer is 0, and let's just walk through why, real quick. The last digit of 100, that's 0. The last digit of 10, also 0. Our function just adds them up. 0 plus 0 is 0. That's the value it returns to the CEO. The logic is solid.
And that brings us to one last question, something to really think about. You now have this powerful first principle for taking numbers apart. We used it to get the last digit, but how could you use this same tool, maybe with a little twist, to get the second to last digit? Or, hey, what about using it to check if a number is even or odd? The tool itself is simple, but its applications, they're huge. And now you're really starting to think like an architect.